Okay, so before I start, this is a QR code you can scan to figure out where to upload your slides for the lightning talks if you haven't gotten it uploaded already. You should also have gotten an email with this link, but this is my final pitch to get everyone's slides in there before that time. So what I'm going to be doing is just giving a sort of what I hope will be a pretty accessible introduction to a lot of the mathematical tools. For a lot of folks who are sort of already deep into this may be a little bit of a redundant experience, but it also might introduce you to a little bit of different notation, different ways of talking about the same ideas you might already be working on. So with that, to give you a sort of overview of what we'll be talking about, we're going to start with revisiting what, as roboticists, we're all pretty familiar with, rotations and homogeneous transforms that are Lie groups you already know and love. We'll then start talking a little more abstractly about smooth manifolds, the kind of spaces that we usually work in these contexts, and bring in a little bit of fundamentals of Lie groups, so how we can think more abstractly about continuous transformations in general. And then start talking about how these Lie groups can act on other manifolds, so how we can describe symmetry of data defined on spaces that may not themselves be Lie groups. We'll then come to our two most common flavors of symmetry, equivariance and invariance. And then at the end, I'll give a little bit of a sampler of how these ideas are going to play out in a couple of different domains in robotics that will sort of serve as a preview of what the other speakers are going to talk about in a lot more detail later. Please ask questions during the talk. Just raise your hand, interrupt. I tried to leave time for questions, so please do that. As this is not a research talk. This is a casual sort of conceptual overview, so go for it. So whether or not you work in control or estimation or perception or something completely different, no doubt you've seen homogeneous transforms at some point, right? Where we talk about how different coordinate frames in a robotic system are related according to their rotational and translational offsets, right? And this sort of overall homogeneous transform is made up of a positional offset between the frames and a rotational offset, and that rotational offset lives in this space of rotation matrices SO3, right? And this should all be pretty familiar stuff. And I'll sort of assume that we have a basic familiarity with some of these ideas around 3D rotations, and think about how we can abstract that to a sort of more general setting. And to do that, we'll typically be thinking about spaces that we call smooth manifolds, which, as many of you are surely familiar with, these are spaces that sort of look like Euclidean space or look like Rn when you look at a very small or maybe even pretty big region of them, but maybe globally they have a different structure. And what's really, the reason we study these spaces is that we can do calculus in these kind of spaces because they have these sort of local structures we need without assuming that we have that structure globally. And in this slide, we'll sort of think about these manifolds as being some sort of submanifold of a larger Euclidean space, an ambient space. And we don't need to do this, but it'll let us state the definitions a little bit more succinctly for today's purposes. So of course, the manifold we're probably most familiar with is the sphere in 3D space, which is just a set of all points with unit norm, right? And for this manifold or for any other manifold, we can talk about its tangent space, which is sort of the collection of all the vectors that sort of lie tangent to that surface when we're thinking in this sort of ambient space perspective. But we can also state that a little more abstractly like we've done here. We can think about the tangent space as being sort of a set of equivalence classes of curves. So take all those curves in our manifold for some small open interval that at time 0 exactly hit that point on the manifold, and then think about what its velocity is at that point, and collect up all of those entries, and that's a way to sort of formalize the tangent space with that as sort of direct reference to this sort of embedding idea. Once we have this sort of construction of a tangent space, we can start to think about taking differentials of smooth maps, which is sort of like how we think about ideas very similar to the Jacobian that we might be very familiar with from sort of a robotic kinematics setting in a more abstract way that applies to sort of any smooth map. And to do this, we say, okay, take some tangent vector in our original manifold and pick some smooth curve that at time 0 is exactly at that point m, and its velocity matches that tangent vector here, which we'd like to compute the differential map of. And then take the derivative of composing that curve with this map between the manifolds, which is just like saying, take this, at least in this ambient space, like taking the usual derivative we're familiar with of that sort of composed map, right? But more broadly, what this lets us do, oh, there's a question. Yeah. Yeah. So in this slide, we're defining derivatives using this ambient space, this embedding, right? So in this slide, we're not assuming we have a chart. We're assuming that we are computing this like composed map here, which would then be a map from time into this manifold M, which is a subset of this bigger Euclidean space, and then differentiating that map in that Euclidean space. So it's sort of like a maximal coordinates perspective. You could define it using a local chart, or you could define it totally intrinsically, but we're going to not go too deeply into that today. Yeah, cool. And so really this lets us start to think about how data defined, or how a map between two manifolds also induces sort of maps between the tangent spaces, or the tangent bundles of these two manifolds, which I didn't mention on the slide, but it's sort of the collection of all of these tangent spaces. So to talk about symmetry, we'll use these algebraic structures called groups, right? Which is basically a set G along with some operation that takes two elements of the group and returns some other element of the group. And it has to have three special properties. The first is associativity. So if we operate the group operation on A and B first and then add C, we'll get the same result as if we did B and C and then added A on the left, right? Also, the property of identity, so that there exists some element of the group so that no matter which element we operate on with it, we get that other element back, right? So for the space of rotation matrices we mentioned already, this is just the identity 3x3 matrix, right? Also the idea of inverse. So for every element in the group, there's some other element that when we put them together, we get back that identity. So if we have these properties, we have a group. And so just to give you a quick example, we can think about the permutation group, which is the group of matrices where every row and column adds up to 1, and there's exactly one entry that's non-zero. So we could say that every row and column is a one hot vector where there's only one non-zero entry and it equals 1. The group operation here is just matrix multiplication, so we can multiply these guys together. And the inverse is just the transpose. So if I take this permutation matrix here and I take its transpose and I multiply those together, I'll get back this identity matrix here. So we'll be particularly interested in, well, many of us will be particularly interested in Lie groups, which are groups that are also smooth manifolds, essentially. And so while the permutation group I showed in the last slide, you can think of it as a discrete group, we're interested in these sort of continuous transformations that allow us to describe sort of the smooth symmetries we often see in space. And so for those groups, we'll expect that the set itself is a smooth manifold and that the operations for the group operation and the inverse are smooth maps as well. So a simple example, this would be the 2D rotation group, right? So these 2x2 matrices that we can sort of parameterize just in terms of this rotation angle. And if we were to work out the group operation using matrix multiplication, it would look something like this, where the angles add together, and the inverse is just the negative angle of that. And all of these are smooth operations, and this lives in this smooth manifold. And so this is an example of a Lie group, right? Of course, there's lots of other examples that we'll be encountering today. So the rotation group in any dimension, not just the two-dimensional one here. We could also think about Euclidean spaces as being both smooth manifolds and Lie groups. So any Euclidean space is sort of the prototypical smooth manifold in some sense. But it also has this Lie group structure when we think about addition. So the operation in that group is just adding vectors together, tip to tail, like you would have done in a undergrad linear algebra class. We could also think about, let's say, the positive real numbers under multiplication, because every positive real number has some multiplicative inverse, which when you multiply them together gives you 1, right? So a question that I sometimes get from younger students is, well, is every manifold a Lie group? Is there some way to put a group operation on every manifold? And the answer is definitely not. So there are some manifolds that are not Lie groups, and we can show that in a number of different ways. But one observation, if you have a little more familiarity with this, is that all Lie groups are parallelizable, which means their tangent spaces can sort of be expressed globally as the span of a certain number of vector fields. And not all manifolds are like that. So probably the one everyone's familiar with that's not a Lie group is the two-sphere. So just to keep that in mind, that's sort of a special structure on top of the manifold structure. And all the examples that we'll talk about in this talk, at least, are what are called matrix Lie groups, or at least they're isomorphic to them. They can sort of be represented equivalently as a matrix Lie group, which means that we can think about them as some sort of subset of this group of invertible n by n matrices. And the group operation can just be expressed as multiplying those matrices together. And there are non-matrix Lie groups. We usually don't encounter them in robotics, so I'd love if someone could give me an example of where that's not true. But most of the Lie groups we encounter in robotics are these matrix Lie groups, which often really simplifies the kind of calculations we want to do. So often when we're thinking about equivariance and invariance and symmetry in general, what we're interested in is working with group actions. So group actions are a map from some Lie group and some smooth manifold back into this smooth manifold with a couple of particular properties. So the first is identity, which basically means that if I take the identity element of that Lie group and I plug it into this group action map, and I transform any element in the manifold, I better get that element back. So in other words, the action of the identity has to be, nothing happens. The second property we sometimes call compatibility, which basically is to say, if I start by acting with some element G2, and then I also act with G1, I want to get the same result as if I had first multiplied together G1 and G2 using the group operation, and then acted on M with that result, right? And here I've stated these properties for what are called left actions, which are actions where we're doing this multiplication in this order, where the one on the left here is the one on the left here. We also think about right actions, where that second property is just switched around, right? So we call it a right action because we're sort of multiplying on the right by this other element, G1. Questions? Can you, like a specific example of an action? I have one on the slide in a moment, yeah. And often it's convenient to write this group action in this form. We've sort of contracted this argument G, and we're sort of thinking about this as a family of transformations of M, a family of actually diffeomorphisms, so smooth invertible transformations of M parameterized by elements of that Lie group. And if you're a little more familiar with group theory, you might notice that this is actually a homomorphism from the Lie group G into the diffeomorphism group of M, but I won't go too deep into that. So here's my example. So we can think about the action of SO3 on the 3D space, right? And in this case, I'm choosing to write that just as R is acting directly on this vector. So we're just rotating every vector in space by some amount, some rotation matrix, right? And so before I go on, this is a left action, because if I were to compose another, let's say R2 on the left side here, I would get, R2 times R1 times X. On the other hand, if I defined this as a right action, I could, for example, let me see if I can use this tiny square of whiteboard here. I could write, let's say if I defined the action as, ooh, that doesn't work. I don't think this is a whiteboard marker, so I'm not going to put it on the board. Okay, well, I can't write, but that's okay. If I define this action instead as R transpose X, you could imagine then phi of R2, phi of R1 X would look like R2 transpose R1 transpose X, which when you transpose, you also flip the order of the matrices. So you get R2 R1 transpose. I'd have to write out the details, but I hope that answers your question. So like I sort of alluded to before, the reason we're interested in group actions is really because they allow us to describe symmetry of data that's defined on some other manifold that's maybe not a Lie group. And when I say data, I don't just mean data in the sort of machine learning sense. I mean whether it's it's a function you've defined, it's some vector field, some thing we want to work with and analyze and exploit the symmetry of, which may not be defined on a Lie group that has this group operation. So group actions sort of allow us to bring these tools to those spaces as well. And so to give you a little bit of context, M could be the state or input space of a control system. And so we want to think about what happens when we sort of move to different states and inputs using elements of the group. It could be the input or output space of a regression problem. So say there's some function we want to learn from, let's say, some manifold M to some manifold N based on samples of that data. Or it could also be, let's say, the state or action space of a Markov decision process if we're thinking about learning optimal policies, let's say. And so this will maybe also answer this question about left and right actions a little further. If we take any Lie group G, it kind of comes equipped with a couple of group actions out of the box. Excuse me. So the first one's called the left automorphism, which is just the action of G on itself. So here, if I take, I've written it in this sort of contracted notation, right? And the left automorphism corresponding to each element G transforms every element H in the group by just multiplying on the left, right? Whereas the right automorphism is an action of G on itself given by just multiplying by G on the right over here, right? And so, like we may be familiar with in robotics, rotations in 3D space don't commute, right? And so often it's, there's a distinction between these. There's one more group action that is pretty important that shows up, and that's called the inner automorphism. And this is a left action of G on itself, which is just sort of the composition of the left action and then the right action, but for the inverse element, right? And it's pretty easy to verify that if we just compose this twice, we would get, we can verify this is in fact a left action, the way we've defined it. And so, like I was just alluding to, in groups where the operation is commutative, we call these groups abelian. And in those groups, the left and right automorphisms are actually the same map because GH equals HG. And so for that reason also we can see that the inner automorphism is the identity, right? Because these two just cancel if they're the same map. And so to give an example of an abelian group would be the 2D rotation group that we just talked about, right? Because if I rotate some angle, there's no way to say, oh well, if when I wrote it out with the R of theta, those things just add together, and addition is commutative, right? On the other hand, 3D rotations or even 2D pose transformations, so sort of homogeneous transforms in 2D space, don't have this property. The order in which you compose them matters, right? And so those are non-abelian groups. What am I doing on time? Pretty good, I think. Please keep interrupting with questions, though. Yes, please. As the phi, yeah. L is a particular instance of phi, so it is a group action. It's just a very special one, so we give it a special name. Yeah. Any other questions? Great. So every Lie group also comes with a friend called its Lie algebra. And this Lie algebra is actually just the tangent space of the group at the identity element. So we can think about, in this group, taking that identity element and thinking about all those tangent vectors there. And because it's so special, we'll give it this special notation here, this math frac G here. And you might be wondering, okay, why do I care so much about this tangent space? And the reason is that every tangent space of the group is sort of isomorphic to this Lie algebra math frac X. So I've written this here as saying, imagine I took every element of this tangent space and I mapped it through the differential of the left action or the right action, I would get the tangent space at this element G. So it sort of establishes this correspondence between tangent vectors at any point on the group and tangent vectors at the identity, which is sort of at the heart of a ton of what we do with Lie groups. And so if we have some curve G that's moving through the group, we can question. Yes. Yes, so great question. So the first thing I want to clarify is this I'm sort of using, I'm mapping a set through a function. So for every element of G, I'm going to individually map it through the function and then collect everything. And that function I'm mapping it through is the derivative of this map LG, or the differential. So the way I define the differential in the very beginning of thinking about how, if you have a curve in one manifold, and at a certain point it's got a certain velocity, if you map that curve through to the other manifold, at that same point in time, it's going to have some velocity. And that would be the tangent vector that we would sort of pick out as the one that we're mapping forward into. Sorry. One more time. So LG itself acts on group elements, but the differential, so almost I would put parentheses, I would write D open parentheses LG close parentheses. So we're taking the differential of this contracted map LG. I probably should have walked through that more bit by bit. So thanks for asking that. More questions?
So like, how can I interpret like the first line of the spectral piece with the sound with that?
The first line?
Like the G.
Oh yeah. DLE is the identity map in this. Let me think about that for a second. It's not the identity map. It's just that this is a special case in the sense that G equals E. So if I put E in here, yeah, DLE is the identity map in this setting because it.
E is the identity
Yeah.
map.
LE is, and the differential the L. Yeah. There you go. That's right. Yeah. Exactly right. Yeah. Thanks, Rob. So if we have some curve, we can express the velocity of this curve using these ideas. So the first way to do that is to define the body velocity, which we do by taking this curve G and using DL inverse of this tangent vector at G. So this guy here lives at T sub GG, right? This G dot in here. And we're going to take the inverse of this. So we're going to bring this DLG over to the left side of this equation and bring this guy back into mathfrak G, the Lie algebra. So this is stated very abstractly to try to sort of abstract this, but this is just like saying for a rigid body moving in space, we can talk about its angular velocity, which lives in the Lie algebra of SO3. And we could represent that angular velocity in the body frame. So sort of what your bias-free IMU would measure on the robot as it's spinning, right? But on the other hand, we could take that same vector and we could express it sort of in the world frame. And that would be what we would get if we did this sort of right action. This sort of, how is the, like what is the, if I took, you know, you can think about the angular velocity as an instantaneous axis of rotation, right? And if I represented that axis of rotation in world frame coordinates, that's sort of like this. I don't know if I explained that super well, so feel free to ask questions. What's that? With T? Where's the typo? Yeah. Oh, sorry. Yes, this should be SPAT. Sorry, that's a typo. Thank you. Thank you. Yes. Thank you. Yeah. Thank you. Yes. And so there's one more map I want to talk about, which is an action of G on its own Lie algebra, which is called the adjoint representation. And the adjoint representation is just the differential of the inner automorphism we described before. So we defined this inner automorphism IG, right, which is just LG RG inverse. And then we took its differential and we evaluated it on the Lie algebra and we get this guy. And that might seem a little convoluted, but the reason it matters is it essentially converts between spatial velocities and body velocities in this way. So this is kind of like saying, well, if I know my angular velocity in the body frame, I can multiply it by the rotation from body to world to get the world velocity. And that's exactly what this equation is, just in a little more abstract terms. Okay, going forward, we can start to talk about properties of group actions. So we can ask sort of what structure does a group action have that maybe a different group action wouldn't have, and what can we do with it? And there's two I want to talk about in this talk. One is free group actions. So we say a group action is free if for every element in the group that's not the identity, this map phi contracted with G has no fixed points. So let me unpack this a little bit. What this means is, well, let me first say, we define group actions so that the identity always does nothing, right? It doesn't transform any points. So we got to exclude that. But what we want to say is if I act in a non-identity way, I want every point in the manifold to move, right? So there's no point that's sort of untouched. And I'm going to give some examples in a second. On the other hand, we can talk about transitive group actions, which are group actions so that if I pick any 2 points in the manifold, there is some group action that takes me from the first point to the second point, which is not always true. And I'll give you examples in just a moment. And these are two really important properties that start to sort of capture what is the structure that this group action provides. So here's my first example. We already talked about this group action, actually. It's the rotation of vectors in 3D space by some rotation matrix R. So for every vector x in R3, we're just going to rotate it by R, right? And I want to ask, is this guy free and transitive? So maybe I'll do the first one, and then I'll try to get your help on the second two examples I'm going to give. So the first one is, this is not a free action. And the reason I know this is that rotations preserve the origin, right? So no matter what rotation matrix I choose, the origin is always a fixed point of that map, phi r, right? On the other hand, it's also not transitive because rotations preserve norms, right? And so if I pick some vector x1 with some norm, there's no way I could rotate it to a vector that has a different norm, right? There's just no way to do that. And so this is not a transitive action. Questions on that? Please. It's a property of phi. So I could specify, I'm going to give you examples that have the same group, the same manifold, but are not free, or one or the other, but are not necessarily free or transitive. So it's really a property of the action. I mean, I could define, you could ask a question, does every manifold group pair admit a free action or a transitive action? I have to think about that, but like, okay, there we go. Okay. Yeah, I don't know the answer. Great, well, I can't solve that then, but in general, it's a property of phi itself. Yes. So, for example, I could restrict this action to the unit sphere, which is what I'm about to do, actually. So let me try to run that one through. So here I've taken the same map, at least it looks like the same exact map, but I've now restricted its domain to the unit sphere, right? And so now the question I'm going to ask you guys, is this a free action? What do you guys think? What do you folks think? Please.
Yes, but now you don't have the order.
Exactly right. So every point on the sphere is going to move if I rotate it by some rotation matrix that's not the identity, right? So not free. Sorry. I did the example 3 is the one I was just talking about. Sorry. Okay, sorry. Going back here. This is not free because if I rotate it by some rotation matrix, any point along the axis of rotation doesn't move. Sorry, I got a little mixed up there. So if I rotate around the z-axis, anything that's on that z-axis won't move, so it's still not free. Questions on that, since I was just very confusing? Okay. On the other hand, this is a transitive action. And this is not a proof, but the reasoning here is that we can always pick an axis of rotation that will bring some point on the 2-sphere to some other point. And my sort of proof, hand-wavy proof, is, well, let's consider 2 points x1 and x2 that are not along the same line for now. We can always take the cross product of those 2 points and figure out an axis of rotation that's perpendicular to both of them that will rotate one to the other. And if they're exactly on that line, we can figure out a special case or whatever, right? So this action is transitive, but because of that analysis there. So I don't know if this has fully answered your question, but we're sort of giving here an example of this is the same group. It's a slightly different manifold, but we can restricted it in that way. Quite, yeah. Yeah, okay, great. Beautiful. Okay, last example here, hopefully I won't mess this one up, is I've now said, okay, let's forget about R3. Let's think about rotating using some, you can think about it as an angle in SO2, right? Or some 2x2 rotation matrix, same thing. And we're going to rotate some rotation matrix by that angle. And we're going to do that in a way we're going to say, okay, compute a rotation around the z-axis by angle theta like we would normally do in robot kinematics. Just stick that on the front of your rotation matrix R, right? So does everyone, any questions about how I've defined the action? Great. So do we think this is a free action? What are your thoughts? What was that? Should be free. And my reasoning is that at most one column of R can be parallel or anti-parallel, meaning opposite direction, but sort of still parallel to this axis of rotation, right? So in the second example, the problem was that this particular point on the sphere is directly along the axis of rotation. But since we're acting on this full rotation matrix that has 3 columns, one of those columns, actually 2 of those columns, have to be not along that line, right? And so this rotation will always rotate something. There's always going to be some movement for every point. Is it a transitive action? What do we think? You say yes? Can you tell me your reasoning? Yeah, I think there's maybe even 2 axes. Sort of the idea here is like we think about representing rotations with Euler angles, right? And even though that's not global, it's getting close, let's say, but we need 3 axes of rotation to produce arbitrary rotations, right? And this is only 1 axis of rotation. So this is definitely not a transitive action because we're sort of restricted. I would say it like this. Say this is our object, and this is our z-axis here. We can only produce rotations like this, right? But we can't produce rotations that move that pen around. Okay, question?
So the example that you just did, how is it different to the second example where you say anything that's on the z-axis doesn't rotate?
Are we asking about free or transitive? Free. So the difference is, you can almost think about it as like, the sphere is like, if I just had this Sharpie, where you can't distinguish how I'm rotating it like this. You can't see that at all. And the issue is, say I'm rotating around z, so this is the vertical axis, and the Sharpie is perfectly vertical. Then the tip of the Sharpie doesn't move at all when I rotate around that gravity vector, right? And so that's an example of a particular rotation that, I know what the problem is. This should say R, not RZ theta. That's my mistake. I must have carelessly copy pasted here because this should be the action of SO3, not SO2. So that's my mistake. Does that answer your question though? Okay, let me say more. So here's our single sphere point. Actually, I'm not going to do it vertical because that's going to it's going to muddy things a little bit. It's at some random direction. Okay, yeah, and so this guy is rotating, that guy doesn't move. On the other hand, you can think about a rotation matrix as having all of these vectors here, right? Like each column is one of these 3 vectors. And so if I rotate around the first Sharpie, these other guys are going to move even though this original one doesn't.
So it's not along the axis that should not be moving.
Yes.
It's anything.
It's anything in this space M, which in the first example, in example 2 was the sphere, but in example 3, it's this full rotation matrix. Question?
Clarify, what do you actually mean by fixed point here? And
Yeah.
That's maybe what's getting people to stumble. Like when I think of a fixed point, I actually think of like x dot equals f of x, set x dot equals to 0,
Yeah.
and solve for fixed points.
Yeah.
But there's no dynamics here.
Yeah. So
What do you actually want
yeah.
fixed point?
So for a map f m to m, a fixed point of f is some point in that manifold so that f of m equals m.
And a equals p.
Yeah. Yeah. Well, yeah. Sorry. Better way of saying it. Yeah. I was thinking lowercase m, but f of p equals p is a better way of saying it out loud. Other questions? Please.
Right. It is not about this one point for.
It is. You're right. It's just that I wrote it up here, so it was confusing. But you're right. This is. I don't want to get too deep into this. I don't want to confuse people, but you're right. That is still. Yeah. Yeah, it's true. It's just this is almost example 4 because I just these 2 things are not consistent with that. So I don't want to confuse people, but you're correct, 100%. Yeah. Okay. Moving on. Now that we've talked about these properties, I want to talk about something called the orbit of a given point. So given some point little m in M, we define its orbit as all the points the group action can send it to. So we take every element of G and we just act on that point M and we see where things end up, right? And that's called the orbit of that point under this action. So you can think about orbits almost like partitioning the manifold, right? You could ask like how do I think about what orbits look like? Well, it's if I take some point and another point is in its orbit, then like they're friends. They're in that element of the partition. But if it doesn't end up at somebody else's orbit, well, it might have its own friends. And we can sort of divide the manifold up into the collection of orbits. So in particular, if this action is transitive, there's only one orbit, right? That's sort of the definition of transitive, is that the group action can take you from where you start to anywhere on the manifold, right? So there's only one orbit. To make a little more formal what I said before, we can sort of define this equivalence relation, where if we take any 2 points in M, we say that they're equivalent, that's the notation here, if one is in the other's orbit. And it's easy to check that M1 in orbit of M2 is if and only if M2 is in orbit of M1, right? And so we can then sort of think about a quotient space, which consists of all of those orbits. So every element of this quotient space, which we notate as M mod G, is one of those orbits. We can sort of think about taking all of the points in this manifold and sort of projecting them down into this quotient space where the only points we care about, we don't distinguish between individual points in an orbit, we only care what orbit are you in. And this quotient space in general can be really messy. So it depends a lot on the properties of phi, what kind of structure this quotient space will have. But I'll give you a little sort of taste of what that might look like. And so one of the things we can say is that if phi is free and G is a compact group, roughly speaking mean it doesn't go off to infinity. So SO3 is an example of a compact group, but SE3 is not because the translation just goes off to infinity. If we have these 2 things, we can say that this quotient space actually has a sort of uniquely defined smooth manifold structure that we can play with. It's sort of There's a designated smooth manifold structure that's consistent with the smooth manifolds we started with. And actually, this happens in a slightly more general setting where phi is free and proper. So it's not required that G be compact, but we're not going to talk about that today. And so in these settings where we have these properties of phi, we can really work with this quotient space in terms of doing calculus on it in the same way we would on any other smooth manifold. But that won't always be the case. And so that's something we sometimes need to analyze when we work with these kind of symmetries. So I can give you a quick example, and I'll keep going because I'm going to run out of time, which is to say, if I take that action of an angle on SO3 that I talked about before, the quotient space that we get there is actually the sphere. And to give you a sort of proof by hand waving here, here's my rotation matrix one more time with my 3 axes. And I'm going to say, well, the orbit, if I rotate around this axis, the orbit just looks like this, right? There's all the points that rotate here. And I'm going to call all of those the same. In other words, I'm going to get rid of these 2 axes and completely ignore them, right? And what I'm left over with as I apply all sorts of rotations to this guy are just points on the sphere at the tip of this pen, right? And so I can give that quotient space the structure of a smooth manifold too. We've talked a bunch about group actions. I gave you a bunch of examples of groups, and you probably know some other ones too. But we can also start to really compose these things and build all sorts of crazy groups out of other groups. And so say we have 2 Lie groups, G and H. They each have a group operation. They each have the set that they consider. We can construct new groups out of these groups in sort of 2 standard ways. The first way is just the direct product of these groups, which we write in this way here. And this is the group whose elements are G comma H, is sort of a Cartesian product of the sets. But the group operation acts component-wise. So to multiply G1H1 with G2H2, we just multiply G1 and G2, and we multiply H1 and H2, right? And now we've gotten a group whose dimension is the dimension of G plus the dimension of H, and they sort of work together, right? That one's pretty easy, but we can also define something called the semi-direct product. So if we have a group action of G on H, the semi-direct product, which we notate with this funny little symbol here, is the Lie group whose operation looks like this. And so when you stare at this, it might be a little bit like, well, where the heck did you get that? But let me walk through here. So we said G is just going to do its own thing. It's just going to interact with its friend G2. G1 and G2 are going to do their own thing. But for H1 and H2, what we're going to do is we're going to first let G1 act on H2, and then we're going to combine it with its friend H1, right? And so we could check real quick that this is a valid group operation and whatever, but I hope you'll believe me on that front. Sorry, before I go on, when is a semi-direct product actually just a direct product in a trench code? Is there a way we could turn this formula into this one?
Well, the intuition is somehow in phi just allows G1 to disappear.
Exactly right, yeah.
That's the intuition. So that's a special type of action.
Exactly. It's the trivial action. It's the action that does nothing to the thing it's acting on. It's still a valid group action. It still satisfies the definitions. But if phi just is totally lazy and does nothing, that phi sub G1 is the identity map, and we just get H1, H2, right? Okay. What's the difference between R3 cross SO3, and here I mean it in the sense of this, and SE3, the space of translations and rotations, or rather, not the space of translations and rotations, the space of homogeneous transforms that we are familiar with in robotics? Well, as a smooth manifold, nothing. They're the same set. They sort of have equivalent differentiable structure, but as a Lie group, in terms of the group operation, they're different. And the difference is that SE3 is actually the semi-direct product of SO3 and R3 here. And in particular, it's the semi-direct product for this action phi given by this here. So we can sort of verify this by taking 2 of our homogeneous transforms and multiplying them together using matrix multiplication. We'll get this. And in fact, it's not too hard to see that, well, I've got R1 times X2 here. That's just phi R1 X2 as I've defined it here. And then I'm adding X1. And adding X1 with this is just the group operation in R3 because of the group operations addition, right? So this is sort of a question I've gotten from a lot of younger students of, what's the difference between these two? And the whole answer is they're only different in the group operation. In terms of the manifold, they're the same, but they have a different group structure. Okay, I'm about to run out of time, so I'm going to go fast. So there's two flavors of symmetry we'll talk about in this workshop. And I won't belabor them too much because I think you'll hear a lot about them later today. But we're going to start with some map F from M to N. These are both manifolds, and actions on both the domain M and the codomain N, right? We say that F is invariant with respect to the group action phi if I get the same result if I compute F or if I first transform the input with the group action and then compute F for every element G in that group. So it makes sense because F is sort of invariant. It doesn't vary when we compose it with this group action, right? On the other hand, we'll say that F is equivariant with respect to both of these group actions. If I get the same result, if I compute F and then transform the output in the domain in the codomain space, or if I first transform in the domain using this other action and then compute the function. We'll call that equivariance. And so we can illustrate these two ideas in what are called commutative diagrams. So what I mean here is computing F for every element of N, computing F will give me the same result as first applying phi G and then composing that with F here. So you read these commutative diagrams as sort of take all the paths in the diagram, all the directed paths in this directed graph, and compose all those functions, and then take every element in the space at the node and see if you get the same result on all paths that start and end at the same point, right? On the other hand, equivariance looks like this, where computing the function and then transforming the output gives me the same result as transforming the input and then computing the function. So in particular, invariance is just equivariance with that trivial action we were just talking about before. So suppose that this psi here is just the identity map on the right here. I can sort of squeeze these two guys together and F will go right there, right? So invariance is a special case of equivariance. Okay, with the very, go ahead. Yeah. Yeah, so I use this word, people may disagree, but I use this word sort of informally as an umbrella term for invariance and equivariance. Some other people may have thoughts on trying to give this a more precise notion, but even like, I'm recently working on some things related to sort of weak notions of equivariance, and I would describe those as symmetry, but not precisely these two diagrams here, is my viewpoint at least. But I'd love to hear others throughout the day. Okay, in like the last 3 minutes, I'm going to give you a quick sampler of what these symmetries might look like in a couple of robotics domains, and you'll hear way more about this throughout the day, right? So consider a perception task. Here I picked a really simple one, designing an edge detection filter for square grayscale images. So we'll think about this as a map from this pixel space, RK by K, to this class space of edge or not edge, right? And we're going to define an action of this discrete group called the dihedral group, which consists of all sort of rotations and reflections that preserve the vertices of a regular n-sided polygon. So here our polygon is a square, because we're thinking about square images. And think about all the ways we could rotate that square or reflect that square in order to keep it the vertices at the same point, right? Now let's think about our edge detection filter. It should take an image like this, and it should map it to an image like this, where we've called out all the edges, right? Well, if I were to rotate this coin, all of the edges should rotate in the same way, right? And so what we would like to have happen is that edge detector predicts this image when I rotate it, right? This is exactly the same. All I've done is rotate that output, right? We want this edge detector to have this property. So it's sort of a commutative diagram in image form, right? And so that's the sort of desirable property. I want to remind you that one of the successes that convolutional neural networks, what they owe their success to is the fact that they have translational equivariance. So in other words, shifting the input will also shift the output of a convolutional filter, maybe for a much more complicated one than this one. And the question is sort of what about rotations and reflections? These are other transformations which might also want to preserve these things, right? And so a common approach, which is a whole line of work I'm not going to go into detail about, is essentially designing neural network architectures that explicitly enforce equivariance constraints for other transformation groups besides translation, often through what are called group convolutions, or sort of generalizations of convolutions. And Mani's talk later, I think we'll talk a little bit more about this in detail. Another quick area, reinforcement learning. So suppose I have some Markov decision process, which has a state space S, an action space A, a reward R, and some transition dynamics, which tell me given if I'm at some state S and I apply action A, what's the distribution of future states at the next time step? And suppose I have some group actions on the state space and the action space. Well, it's a fact that you can find in the literature that if this MDP has certain symmetry, its optimal policy and value function have some corresponding symmetry. So if the transitions are equivariant in the sense that if I transform the state in action and then compute the transitions, I should get the same result as if I compute the transition probabilities for a transformed sort of future state space. And the reward being invariant is sort of, just if I transform the state in action, I get the same reward. And in that case, you can prove that, with some other assumptions that, or some mild assumptions on the spaces we're working with, that the optimal policy is equivariant and the value function is invariant. And so a common approach, this is a sufficient but not actually necessary condition for this line here. A common approach then is to constrain the value in policy networks in such a way that enforces these symmetries and then apply our standard RL algorithms, but with these particular structured networks. Another approach, though, which is slightly different, is essentially to use these symmetries to construct what's called an MDP homomorphism, which essentially projects this down to a lower dimensional MDP and then solve it with standard methods. And I think I'm essentially out of time, so I'm going to breeze through the last 2 slides because we're going to talk a lot more about them in the next couple of talks. Actually, I might just, for the sake of time, skip this and let, this is just talking about the global error, and let this be discussed in Stefan's talk. I think he's going to talk about this too, right? Okay, so I'm going to skip this slide. The last thing I'll say is, for a general mechanical system or a robotic system, we've all seen the dynamics written in this form. We often call them manipulator equations, right? Where these matrices, the mass matrix, Coriolis matrix, and gravity and input matrix, they all are defined in terms of Q, right? However, for lots of robotic systems, like a free-floating base system, it's possible to write the configuration as the pose of some body in the system, and then the joint angles of the system. And most of these systems are, think about a space robot or a flying aerial robot that's actuated by sort of body fixed forces, where it's propellers or it's thrusters or it's the joint motors themselves. And in that case, we can actually write these dynamics in a simplified form, where these matrices don't depend on the absolute pose here. They only depend on the angles of the joints, right? And this is a consequence of symmetry in the mass matrix, and in fact, the kinetic energy, with respect to an action that acts just on the pose. So sort of if we took that body in the system and we rotated the whole system accordingly, where would it end up? And so this is sort of just one more topic where symmetry will show up across these areas. So just a last slide to close. We talked about sort of the basic tools we'll use to describe, analyze, and exploit symmetry in robotic systems. And Lie groups are sort of the basic atomic structure that we use here. Group actions allow us to describe symmetry of data on other manifolds, not just Lie groups. With a free group action, often we think about invariance along those orbits, which is sort of what showed up in the reinforcement learning section. On the other hand, with a transitive group action, we're often able to obtain global error states, which I didn't talk about, but Stefan will in his talk. And the ideas show up across numerous verticals in robotics. And this is not a complete overview, but I hope it makes the workshop a little more accessible to people who might either be coming into this topic for the first time or might work in one vertical but want to sort of think about others as well. So thanks for listening. And I don't know if there's really time for questions, so maybe we go on to the next talk.